You can also incorporate nonlinearity into the model by introducing interaction terms. You can create interaction terms between two binary variables, a continuous variable and a binary variable, or two continuous variables. Empirically, we see a lot of interaction terms between a continuous variable and a binary variable, because this type of interaction terms has a very special property that is quite powerful in estimating the data. We also see the interactions between two continuous variables fairly often. The interactions between two binary variables are not used very often, but we will go through all three cases for you to get a full picture. Suppose that you suspect the effect of gender gap between male and female differs based on whether the workers have a college degree. You can then create an interaction term between the female dummy and the college dummy to explore whether there is a varying effect of gender gap in wages. To do this, you need to create a college dummy that is equal to 1 if education is greater or equal to 16 years, or 0 otherwise. Before running regressions, we usually start by doing plots to visualize whether there are varying effects between two independent variables. In this case, we plotted log hourly wage against the college dummy to see whether there is a difference in gender gaps between the group that has a college degree versus the group that doesn't have a college degree. In this case, we chose to log the hourly wage because the hourly wage data usually have a very wide range that is characterized by fat tails on both sides. Logging the hourly wage will make this variable more compact. This plot shows that in the group of workers without a college degree, the male workers, highlighted in pink, tend to have a higher log of hourly wage as compared to the female workers, highlighted in blue. In the group of workers with a college degree, the distribution of log of hourly wage is more evenly distributed between males and females. This suggests that the effect of gender gap in wages might change based on whether the workers have a college degree or not. Visualizing the data cannot help us draw statistically significant conclusions. We need to investigate this issue further by running regressions. In Model 1, I regress log wage on both the college and female dummies. From this result, I can calculate what is the log wage for 4 different groups. 2 groups based on whether they have a college degree or not, and 2 groups based on the difference in gender. I can also do a t-test for each of the dummy variable, and the results show that both dummy variables are statistically significant at a 5% level. Based on this result, I can conclude that both the college dummy and the female dummy can be used to explain the variation in wages. In Model 2, I added an interaction term between college and the female dummy. Now the interaction term measures what is the partial effect of college on the gender gap. Be aware that in order to measure the partial effect of an interaction term, you have to first include each of the dummy variables separately in the same regression that measures the mean effect for each of the dummy variable. Adding the partial effect and the mean effect together will give you what is the total effect for each dummy variable in this regression. After including this interaction term, the college dummy and the female dummy are still statistically significant, but interaction term is not statistically significant, as the t-stat for this coefficient is very small. This means that we cannot reject the null that this interaction term is equal to 0. You can arrive at the same conclusion by looking at the adjusted square of both models. Since the adjusted R-square is smaller in the second model as compared to the first model, we believe that the first model offers a better fit for the data. This suggests that we don't have enough evidence to include the interaction term in the second model. Now, how do we interpret the marginal effect of each variable in the regression? Because college dummy and female dummy appeared twice in the second regression model. Therefore, in order to measure the marginal effect of the gender gap on wages, we need to do some calculation. Following the estimations of the second model, when female dummy is equal to 1, then log wage is given by the intercept plus the coefficient on college dummy times the college dummy minus the coefficient on female times the female dummy, which is equal to 1 in this case, plus the coefficient of the interaction term times college times the female dummy, which is equal to 1. Similarly, we can write the log wage when the female dummy is equal to 0. Using the first equation subtracted by the second equation, we compute the difference in log wages when the female dummy is equal to 1 versus when the female dummy is equal to 0. This difference measures the marginal effect of gender gap on wages. This equation shows that the marginal effect of gender gap on wages is going to be smaller when the workers have a college degree, because the partial effect of college on gender gap, as measured by this coefficient of 0.07, is positive. To see whether the gender gap on wages differs in the group of workers who have a college degree, we need to conduct a t-test on the interaction term. In this case, because the t-statistic is very small, we fail to reject a null that the interaction term is equal to 0, stating no differing effects on gender gap. However, just because we fail to reject a null from this t-test, it doesn't mean that the gender gap on wages doesn't exist. To formalize the answer to this question, we can do an f-test by restricting all the variables that contain a female dummy to 0. The result shows that the F statistics is equal to 34.47, which is much higher than the critical value around 3. And therefore, we have enough evidence to reject the null that the gender gap doesn't exist and accept the alternative that the gender gap does exist, because at least one of the restrictions should not be equal to 0. Note that this is still not sufficient evidence for gender discrimination, because our coefficient estimates can still suffer from the omitted variable bias in Model 2. Now let's take a look at the second type of interaction terms. This type of interaction term is created between a dummy variable and a continuous variable. It is arguably the type of interaction term that is used most extensively in practice. There are many situations that you might want to see how a dummy variable interacts with a continuous variable. For instance, you might want to know whether heart attack is partially dependent on age, or you might want to know whether one's credit score is partially dependent on race. In this example, we want to know whether the gender gap is partially dependent on workers' education. In this case, the gender gap is a dummy variable, and workers' education is a continuous variable. To examine the partial effect of workers' education on gender, we need to create an interaction term between the female dummy and the workers' education in order to examine how the gender gap changes as workers' education increases continuously. This plot shows that as education increases, the gender gap on log of hourly wage seems to be getting smaller. The pink dots represent male workers, and the blue dots represent female workers. When the years of education are small, the male workers represented by the pink dots, tend to earn a higher log of hourly wages. When the years of education increase, we start to see more blue dots emerging at the top, suggesting that more female workers start to earn higher wages. This plot seems to suggest that education might cause gender gap on wages to close a little bit. To formally investigate this effect, we need to run regressions on these two variables and their interaction term. In model 1, I regress log wage on both education and the female dummy. In model 2, I regress log wage on both education, female dummy, and their interaction term. Now that the interaction term is between a continuous variable and a dummy variable, this interaction term has a very nice visual interpretation for the data. In model 1, if you write the specification of log wages based on males versus females, then you will have two parallel lines with the same slope, but different intercepts. The slope is the same because the coefficient on education is the same for both genders. But because males on average earn higher log wages than females, the two lines will have different intercepts. In model 2, if you write the specification of log wage based on females versus males, then you will have two lines with different slopes and different intercepts. This allows us to use one regression model to estimate different lines for different groups of workers. And that's why this type of interaction term is used a lot in practice. By adding this type of interaction term, you get to estimate different lines for different groups in the data. Let me show you what this means. The regression outputs for model 1 and model 2 are shown here. Based on the regression outputs, you can write the models that measure the log wage for female workers and male workers based on model 1 and model 2. Based on model 1, the log wage for female workers is equal to the intercept plus the coefficient for female dummy times 1, because in this case female dummy is equal to 1, plus the coefficient for education times education. Combining the relevant terms, we get the log wage is equal to 0.465 plus 0.077 times education. Also, based on model 1, the log wage for male workers is equal to the intercept plus the coefficient for education times education. Because the female dummy is equal to 0 in this case, and hence the female dummy drops out of this equation. In the end, the log wage for male workers is given by this equation here. Notice that these two lines measure the log wage of female workers and male workers have the same slope, but different intercepts. Therefore, you can think of them as two parallel lines with different intercepts. Model 2 included an additional interaction term between education and the female dummy. The log wage for female workers in this case is given by the intercept plus the coefficient on education times education plus the coefficient on the female dummy, which is negative 0.36 times the female dummy, plus the coefficient for the interaction term times education. Combining the relevant terms, the model for predicting the log wage of female workers is given by this equation here. Similarly, the log wage for male worker is shown by this equation here. These two prediction models that predict the log wage for female and male workers, respectively, now have different intercepts and different slope coefficients. Therefore, by adding an interaction term between the female dummy and education, effectively you are fitting two different linear lines that measure the effect of education on log wages for male and female workers. The two lines are shown here. The blue line represents the linear model that predicts the effect of education on log wages for male workers. The orange line represents a linear model that predicts the effect of education on log wages for female workers. These two lines have the different intercepts and different slope, even though the difference in slopes is very small in this case. Now let's see if we should include the interaction term in the model. Before including the interaction term, Model 1 shows that both education and female are statistically significant at the 5% level. After including the interaction term in Model 2, we see that education is still statistically significant at the 5% level, but now the female dummy is only statistically significant at 10% level, because the standard error for the female dummy increased exponentially from Model 1 to Model 2. This is because by including the interaction term in the model, we introduced imperfect multilinearity, and hence the estimated standard error for the female dummy is inflated. Furthermore, a t-test on the interaction term shows that this interaction term is not statistically significant. This means that we shouldn't include this interaction term in the model. The adjusted R-square is consistent with this conclusion, because the first model has a higher adjusted R-square than the second model, and therefore adding the interaction term actually reduces the goodness of fit for the model. Hence, we shouldn't include this interaction term in the model. Suppose that the coefficient for the interaction term is statistically significant, then the estimated gender gap in Model 2 can be estimated using the difference in the predicted log wage for female and male workers. This equation shows that the estimated gender gap is increasing in the workers' education. But since in this case, the coefficient for the interaction term is not statistically significant, and therefore the result of the t-test tells us that we shouldn't include this interaction term in the model. Nevertheless, we can do an F-test to see whether there is evidence for gender discrimination by restricting all the regressors that contain gender to 0. The F statistics is very high, and therefore we can reject the null that both the coefficients are 0, providing evidence to gender discrimination on wages. Again, this conclusion is not final since we haven't removed the extent of omitted variable bias in this model. The last type of interaction term is created between two continuous variables. For instance, you might be wondering whether the effect of education on wages depends on workers' experience or vice versa. To explore this, you can plot the log of hourly wage against education and see how education, experience, and the log of hourly wage interact. Based on this plot, we see that everything else equal, workers with less education tend to have more experiences, and workers with higher education tend to have less experiences. This makes sense, as we know that experience and education are subject to the same time restraint, and therefore they will offset each other. Additionally, we notice that as education increases, workers with more experiences tend to earn higher log wages. This suggests that the impact of education on log wages might to some extent depend on experience as well. Therefore, we can create an interaction term between education and experience to see whether there are varying effects of education on log wages based on different experiences. Regressing log wages on education and experience in Model 1 shows that the coefficients are both positive and statistically significant at 5% level. Adding an interaction term between education and experience in Model 2 shows that education and experience are still statistically significant, but the interaction term is no longer statistically significant. To measure the marginal effect of experience on log wages, now you will have to take the partial derivative of log wages with respect to experience, as given by this equation here. This equation shows that the marginal effect of experience on log wage is a decreasing function in education. Similarly, to measure the marginal effect of education on log wages, you will take the partial derivative of log wage with respect to education, as given by this equation here. This equation shows that the marginal effect of education on log wages is a decreasing function in experience. The t-test on the coefficient of the interaction term shows that we fail to reject the null that the interaction term is 0. And therefore, we don't have evidence to include this interaction term in the model. However, the coefficients on both experience and education are statistically significant at the 5% level. Now let's pause this video to do in-class exercises 7, 8, 9. In summary, we introduced 3 different ways to incorporate nonlinearity into the linear regression model by adding polynomial terms, using log transformation, and adding interaction terms. Since the coefficient estimates for these models are still linear, in most cases, we can still estimate and test for these coefficients the same way as before. The interpretation of the coefficients is model-specific. In the end, you might realize that many nonlinear specifications are reasonable since they capture the underlying data pretty well. Which model you should use in this case depends on your personal judgment calls. You can use the specification that you want to analyze and the specification that makes more sense to you in your application.